The first session of today's day 5 of Qiskit Fall Fest 2025 is a hit, absolutely. And as we move forward with the day, we are all set to continue our learning journey under the guidance of someone who's been making quantum computing feel both fascinating and approachable, also. So, in this session, Dr. Jnan Yalla sir will continue leading us through the core ideas of quantum computing, helping us gain a deeper and clear understanding of how quantum principles are shaping the next generation of computation and innovation. So, let's keep our minds open for lots of knowledge coming our way, our spirits high, and our curiosity alive as we dive right into this session. So, ladies and gentlemen, please join your hands and join me in giving a huge round of applause to warmly welcome Dr. Jnan Yala sir as we begin the day 5 workshop session of Qiskit Fall Fest 2025.
Okay. Hello. Okay. So yes, good morning everyone. So today is Saturday, right? So kinda informal in nature, but yeah, completely all right. Because the thing which matters is the thing what I'm talking, right? It's not the way how I'm dressed. Okay, it's a good one, but still. Okay, cool. So today will be the last session of our workshop kind of thingy. So where I would like to explain about this entanglement in nature, which I've been talking about in the previous session. So in a previous session, I completed or I start with something called as entanglement. So from there, I will just carry on the session, like what is entanglement and how our bell states are classified and what is a bell state first of all and all those things. Cool. So yeah, let's directly start. Why? Because I have very low time today, I guess, up to 12. So that's why I'll just start the stuff. And let's see up to where I'm able to cover it. And then from there, I will give you the resources. Okay, you guys have been asking me about the resources since the first day. And the reason why I did not give or I did not say about the resources is that I don't know where we will complete, right? And from the point we complete, from there, what you can do another, I will provide you the resources accordingly. Cool? So, yes. First is entanglement. So, first of all, what is entanglement? What did you understand by entanglement? What is this? Correct only, but what is that exactly? Two of the qubits. Let us consider two qubits. Let us consider, but it's technically more than one qubit. More than one qubit, what will happen to that? They will be heavily correlated. Two qubits are heavily correlated in such a way that what will happen? Simply to put, the measurement of one qubit will directly influence the measurement of another qubit. Okay. So two qubits are heavily correlated in such a way that the measurement of one qubit, let us consider two qubits A and B, are heavily correlated in nature. So when these two qubits are heavily correlated in nature, what will happen is that if a qubit A is measured, when a qubit A is measured, it gives a significant output, right? So when qubit A is measured, this eventually influences the measurement of qubit B. The measurement of B will be influenced with this measurement. So that is your entanglement. Simply to put, that is the entire meaning behind your entanglement. The measurement of qubit A will directly influence the measurement of qubit B. So that is known as entanglement in nature. Got it? Now, what is the meaning behind this measurement influencing the measurement and stuff like that? Or what is the entire meaning behind this influence the measurement? Very simple. So, what do I mean when I say influence the measurement is that if a qubit A, when measured, gives a particular output, through this output, we can define or we can find the output given by qubit B. So that is the entire deal behind it. So we don't need to measure qubit B explicitly. Explicitly, we don't need to perform the measurement on qubit B. By simply measuring the qubit A, we'll get a single value, right? And by having that value and by considering that value, we can find the measure the output of qubit B. So that is entanglement, and that is the meaning behind this influencing the measurement and stuff like that. That's a simple deal. Now, so there are some entanglement states through which we can say like if it is 0, this is also the 0, or if it is 0, this can be 1 or stuff like that. Okay. So yeah, I will just explain it in a very clear way. Right? Simple. So technically, there are only two possibilities. So there are technically four entanglement states. So which we will call it as bell states, which I will explain right now, like the bell states and stuff. So there are totally four entanglement states, which we will call it as bell states as well. Okay. Now, these four entanglement states gives rise to or breaks down into two possibilities. First possibility is that two qubits A and B. If a qubit measurement is 0, then the other qubit measurement is also 0. Okay. This is one possibility. This is one possibility of your entanglement state. The second possibility is what? If it is 0, this is 1. That is the second possibility of the entanglement states. Okay. So first possibility mein what will happen? If my qubit I measured gives an output as 0, then the entangled qubit will also give me the same answer. Okay, that is the first possible case of entanglement. And second possible case of entanglement is that if a single measurement came out to be 0, then the other qubit measurement will be the opposite. So that is the second possible condition of our entanglement states. And as I said, there are totally four entanglement states, Annankada. This possibility is given by two states and this possibility is given by two states. Okay. So why two states ante? One state is plus and one state is minus. That's a simple deal. Meaning, what is the meaning behind plus and minus in case of quantum? Is it the value or what is it? In yesterday's session, I have explained. It is the direction. What do you mean by direction exactly? It is something called as that word is important. What is that word? Phase. Very good. It is the phase of the value. Okay. It is not the actual value. Actual value is this thing only. If it is 0, this is 0. That is one possible case. And that possible case can be given by two of the entanglement states. Out of four, two entanglement states gives me this possibility. Why two ante? Simple. Out of these two, first thing gives me the same phase and the same value. And the second thing gives me the opposite phase, meaning the opposite angle. But the same value, but with the opposite angle. That's the only thing. Same goes for the opposite stuff as well. Okay, I will explain this very clearly. But this is how the entanglement state behave. And this is how the measurement influences. Okay, now? So that is the entire deal behind it. Now I will explain about bell states. And then in yesterday's session, I also told about one point. What is the one point I told? Entanglement states breaks two properties of physics. What are those two properties? Locality and realism. So, how scientists found that they are breaking the locality and realism? Why it is important is, for example, no one went to Andromeda Galaxy to actually test that, right? And no one did any sub because the humans are there in a perimeter where the light traveling is so fast that the distances or the difference in time cannot be measured yet. Okay, so that's why there is no possible way in order to find the locality. So I can't possibly say that it breaks the locality. So, but how did the scientists actually found that the entanglement is breaking the locality? Are you guys getting the point? So technically, by doing some experimentation or stuff, I can't say that it's breaking the locality. Why? Because the humans are in a perimeter or humans are in the area or a range where the small differences in the distance will not alter the speed of light. So if I'm here and there is some person here only, and if I talk to him, definitely the speed is the speed of the light through which the information is going, something lower than the speed of the light, but approximately equal. But the same person, if I call it in the phone who's in US, he will also seem to be receiving the answer in the same time, but there will definitely be a difference. But the difference is very small that it can be negligible. So approximately the both will be kind of equal only. So that's why there is no possible perimeter or there no possible scope where I can actually do the experimentation to find localities being broken. Are you guys getting the point? So if I have the ability to go to Andromeda galaxy, and then I can say experimentally that locality is being broken, bro, and shipping. But at this point of time, I can't. So what is the experiment the scientists did in order to find the localities being broken? So that's one also we're gonna see actually. But before actually seeing that, we need to know about Bell states. Bell states. So how many Bell states are there? Just now I explained. How many are there? Four. So these four Bell states can be called as phi plus, phi minus, psi plus, and psi minus. Okay. So these are real values. They are not variables. ఏదో ఒకటి పెట్టుకోండి కాదు. We should definitely keep this thing only. So why? Because in yesterday's session I have mentioned something known as plus state, right? So this plus state is what? What is this plus state? చెప్పండి. 0 plus 1 by root 2. This is the plus state. And what is the minus state? 0 minus 1 by root 2. That is the minus state. How I can get my plus state? Correct. What is that? Hadamard gate with ket 0 gives me this one. And Hadamard gate with ket 1 gives me minus state. Okay? Cool. Now, Bell states are also like that they are properly defined states anamata. It's not like just like that. Properly defined states. So, this guy, 5 plus is the 0 0 plus 1 1 by root 2. And 5 minus is 0 0 minus 1 1 by root 2. This is 0 1 plus 1 0 by root 2. And this guy is 0 1 minus 1 0 by root 2. Okay. So these are the four Bell states. 5 plus, 5 minus, psi plus, and psi minus. Now I will ask you one question. What are the Bell states which is responsible to define whether A's qubit is 0, then B's qubit is also 0. So in which entangled state can I say like this? Can you guys get the idea of it? I mentioned you one thing about entanglement. If I measure one qubit, that measurement will influence the second qubit and thereby giving the output of the second qubit and shift right? And I also told there are two possible cases. One case is where both answers are equal. Second case is where both answers are opposite. So if I take the equal condition, which entanglement pairs or which entanglement state is responsible for giving this equal output? 5 plus 5 minus psi plus psi minus. Out of these four, which entangled states are responsible for giving the same output? 5 plus and 5 minus. How you can guess that? Simply look at this thing. You can easily understand that. Okay. So here we are having same notations. Sarana? So that's the basic deal behind it. So this is the simple deal. So by just looking at that, you can understand what is the possible answer is. And you can directly do the stuff. Okay now? Now, what exactly is not and 1 1? Asal 0 0 1 1 ante yen. Before, why? Because before we have seen only 0 and 1. Kada? We have seen about 0. What is 0? What is 0? Cat 0 value ente? 1 0. Yes. Cat 1 is 0 1. Okay. But what is this new guy? Now, let's give rise to, I hope you guys have copied this one. So let's give rise to one new thing actually, which is known as a tensor product. Picture light very easy. That's very easy. It's not very different or something. Very easy, straightforward it is actually. And this tensor product is a linear combination of gates or matrices. Okay, tensor product is a linear combination of gates or matrices. For example, if I'm implementing three gates sequentially, if I'm implementing gate A, gate B, and gate C on 0, get. Meaning is this guy can be written as this on I can write in this way anamata. And this symbol is known as tensor product. Okay, keep a circle, keep an X inside a circle. Okay, tensor product. So multiple, the linear combination of matrices, meaning the linear combination of gates can be written in the form of a tensor product. Okay, now these states can also be written in the form of a tensor product. The combination of states can be written in the form of a tensor product, meaning ket 0 tensor product of ket 0 give rise to ket 0 0. Okay, na? So when I write that 0 0, ket 0 0 and rasnapudu, the meaning behind that is this one. Ket 0 tensor product of ket 0. That gives me rise to 0 0. Then what is this? Ket 1 0 ante enti? Ket 1 tensor product of ket 0. Okay? This is not commutative in nature. Keep that in mind. This is not commutative. What do you mean by not commutative? A tensor product of B is not equal to B tensor product of A. So please keep that in mind. That's why when I say ket 1 0, it is only ket 1 tensor product of ket 0, but not ket 0 tensor product of ket 1. Both are different. Okay, now? Now, how I can find this one? Okay, I talked about tensor product, but how I can find a tensor product? Very simple. What is 0 vector? Ket 0, 1 0, right? So when I say tensor product, it is nothing but, for example, if I go 0 0, it's nothing but ket 0 tensor of ket 0, which is nothing but 1 0 tensor of 1 0. Okay? So it's something like this. What is this? How to do this? Really, people will say a lot of different methods, but the easiest way, direct, that easy way is this one. First matrix is there, na? Okay? Second is there, na? This. Over. Answer. So this is your tensor product. Okay? This into the entire matrix, the second value into the entire matrix. That's it. Tensor product is done. So what is the output? Right? 1 into 1 0. What it gives? It gives 1 0 only. 0 into 1 0. It gives 0 0 only. Got it? That's all. Tensor product is over. Adavainda, this is a simple way in how you can do a tensor product. Direct approach. You don't need to do the entire thing. Simply, there will be two matrices, right? Each element into the complete matrix. Each element into the complete second matrix gives rise to the tensor product. That's it. Very easy and very straightforward. Okay, na everyone? Done? Understood this one clearly? Cool. Now, in a similar way, I can do all the stuff. So when I say 0, 0, it is nothing but what? 1, 1, 2, 3. When I say 1, 0, it will be, try to do that. So 1, 0 gives like this. It will be in this format. So when I say 0, 1, it will be in which format? And when I say 1, 1, it will be in 0, 0, 1, 0, 1. Okay, I don't believe you. Thank God I did not believe you. Okay, so this is how the states look like. Okay, now? So this is the this is not entanglement state. These are nothing but called as 2-qubit states. These are called as 2-qubit states. And the entanglement pairs can be achieved by using the 2-qubit states. So why? Because we are working with 2 qubits, but not a single qubit. The single qubit states are 0, ket 0, ket 1. They are single qubit states. But as I'm working with 2 qubits, they come under my 2-qubit states. Okay, now? Understood? Simple, straightforward stuff. Now, first step of entanglement. So now you are clear with the belt states. So if anyone asks you belt states, these are the belt states. Phi plus phi minus, psi plus psi minus. They are known as belt state. Now, how I can prepare the belt states? So how I can prepare belt states is directly equal to how I can create my entanglement states. So if anyone asks you to create a superposition state, what you will do? Use a Hadamard gate. So if you use a Hadamard gate, you can create a superposition state. If anyone asks you to create an entanglement state, they will come and they will be like, bro, I need to create an entanglement state. How? At the time, how you can do that? And very simple. First, let me create 2 qubits. Okay. And create a superposition of first qubit. Creating a superposition of my first qubit. If I apply a Hadamard gate, I will create a superposition of the first qubit, thereby making it in a superposition state. Now, right now, it's in this particular state. And this guy is still in my 0th state. Now, if you apply a C0 gate, now if you clearly apply a C0 gate, this thing will become a 2-qubit state. Okay. So as it becomes a 2-qubit state, this gives rise to something called as a phi plus state. Okay. If anyone asks you to develop a entangled state, the first step is to use a Hadamard gate. When you use a Hadamard gate in the first qubit and a Q naught, and the qubit starts from 0. So that's why the first qubit is Q naught, second qubit is Q1. Okay. So first make the Q naught, make the first qubit go into a superposition state. And after the first qubit goes into a superposition state, keep a C naught by keeping that superposition state as a control and this guy in the this one. Okay. And try to do this particular thing. You will get the output as a 5 plus state. So what do you meaning by 5 plus state? Simple. This is what 0 0 plus 1 1 by root 2. Right. Now, what do you mean by 0 0 plus 1 1 by root 2? So what is 0 0? So what is 0 0 state? How does 0 0 state look like? 1 0 0 0. Okay. This is the 0 0 state which we've seen before. And what is the 1 1 state? How the 1 1 state looks like? 3 zeros followed by a 1. 0 0 0 1. So 5 plus is nothing but 1 by root 2 of 1 0 0 1. Okay. So meaning very simple. This is the 5 plus state I have mentioned. Yes or no? What did I do? I simply expanded the guys. That's it. Meaning get 0, 0, I defined it in a column format. And get 1, 1, I defined it in a column format. And then I simply did the addition. Obviously, they both are the addition, right? And we got this particular thing. So this is your 5 plus state. Your 5 plus state will look something like this 1 by root of 1, 0, 0. Okay. So that is how your 5 plus state looks like. Sarana, a simple case. Now, how we can actually achieve this one by doing this? So how we can actually achieve by doing this? Very simple. From 0, 0, try to apply each of the case. You will get the answer obviously. Okay. So by just doing a continuous matrix multiplications and stuff, you can easily observe the final answer directly. Got it? So that's how this stuff works. And that's how you can create a something known as a 5 plus state. Now, okay, bro. I created a 5 plus state. Now, if I want to create a 5 minus state, I want to create a psi plus state. I want to create psi minus state. How? So the first entanglement state, which we eventually create or which we always create, is something called as a 5 plus state. So we created a 5 plus state by using a header mat as well as a single C naught. I use one header mat and a single C naught. I created a 5 plus. Very good. How I can create a 5 minus psi plus and psi minus? Very simple, very straightforward. The first step is to create a 5 plus state always. Always create a 5 plus state. So I use a header mat and I use a C naught. I created a 5 plus state. Okay. After I create a 5 plus state, if I want to create a 5 minus state, what I can do? In the second qubit, try to apply a Z gate. If you apply a Z gate on the second qubit, the phase will flip for only which phase? I mean, for which state the phase flip will happen for Z gate? One state. Okay. Right now, what will happen? Up to here, it is like this. Okay. When I'm using Z gate, what will happen? The phase of first state will flip. So after this, the output will look like 0, 0 will not change. It will not affect. But only one state's phase will be flipped, right? So one state phase is flipped. Got it? What is this? 5 minutes. Okay, now? So this is how this thing works actually. So if you want to create a 5 minus, very simple, just keep a Z gate. Just keep a Z gate on the second qubit. It will create a 5 minus. Now, I want to apply this one. I want to apply psi plus. So how I can apply psi plus? So I don't want to draw the circuit, so I will directly do it. So 5 plus is nothing but which C naught on HI for my Q naught. Aneskunta. Q naught and the first qubit, obviously. And 5 minus is nothing but Z on my 5 plus. ఇది చెప్తాను ఇంకా క్లియర్గా ఏంటి ఇది అని చెప్పి. And your psi plus is nothing but x with my 5 plus. And the psi minus is nothing but y with my 5 plus. Now, here I used tensor product of I, but here I did not use anything. Why? Very simple, very straightforward, very easy. ఏంటంటే, if I want to apply the gate to my first qubit, ఇక సెకండ్ క్యూబిక్ నేను ఏమైనా అప్లై చేశానా? Is the second qubit is having any type of operation in this point of time? No. That's why I'll make it something like this. Why? It is a 2 qubit state. So as it is a 2 qubit state, we require 4 I mean 2 qubits కాబట్టి we require 4 states, meaning we require 4 cross 4 matrix, but not 2 cross 2 matrix. But my H is what? H is a 2 cross 2 matrix. But I am applying a H for what? For 2 qubits, meaning for 4 states. అప్పుడు నేను ఆ 2 cross 2 matrix మే I will convert that into a 4 cross 4. So how I can do that? By simply keep an identity for my second matrix. So దీని meaning ఏంటంటే this one. If I apply identity, will there be any change? Q naught. Identity apply చేశాను ఏమైనా అవుతుందా దాని state కి? Nothing will happen. It will be still be the same. So that is the operation what I'm doing. So when I say H tensor of I, the meaning is for the first qubit, apply a Hadamard. Second qubit, there's no change. Just like that. It's staying. Okay. This is a mathematical notation. This is how we need to show it off mathematically. And here I did not use anything. Why? Tensor of I and వాడలేదు. Why? If you want, I can go like this actually. ఇలా వేస్తాం ఇంకా వేస్తే. So we can go like I tensor of Z, I tensor of X, and I tensor of Y. What is the meaning behind it? Meaning is first qubit mein there is no change. I don't want to apply anything to my first qubit. So first qubit is identity. Second qubit mein I want to apply the Z gate, X gate, Y gate and చెప్పాలి. Got it? This is a simple case. Very straightforward definition. When we are dealing with a 2 qubit state, we want totally 4 output states. As we require 4 output states, we require 4 cross 4 matrix. But the Z gate, X gate, Y gate, H gate all are 2 cross 2 matrices, which we cannot apply on a 4 cross 4 thingy. So for that reason, we simply make it identity. Identity tensor of Z is student. You'll get a 4 cross 4 matrix. Okay, why? Because I'm applying it on 2 qubits కాబట్టి. Got it? Got the logic? Simple case. This I defines the qubit through which we are not applying any change. H tensor of I, meaning apply H on first qubit. There is no change in second qubit. Ani artham. So I also mentioned 5 minus is achieved by keeping a Z gate and the second qubit. Kada? That's why I went I tensor of Z. When I go with I tensor of Z, the meaning is no change in the first qubit. First qubit atlane unchu. Second qubit may keep the Z gate. Keep the Z gate in the second qubit. Then it will do the 5 minus. Now, what is the meaning behind this actually? అదే చెప్పరా గట్టిగా. Exactly. So what we are actually doing here, first we create a 5 plus state by using a Hadamard and a C naught. I'll use a Hadamard gate, I'll use a C naught gate, I'll create a 5 plus state. After creating a 5 plus state, what I am doing? Use an X-axis X gate for my which qubit? Second qubit. Got it? So that's the thing which we are doing here. Use an X gate to my second qubit. Thereby it will convert it into a psi plus state. Okay? Now, to get a psi minus state, what is the deal? Create a 5 plus state. So this is the 5 plus state. Create a 5 plus state. After creating a 5 plus state, what you need to do to get psi minus? By looking at this, can you say? Second qubit mein apply the Y gate. If you apply the Y gate in my second qubit, you'll get a psi minus state. Got it? Simple deal. Just by looking at the notation, you can understand what is happening. Okay, now? Now. So this is how you can prepare a and belt states or called as an entanglement states. So these are known as maximally entangled state actually. And meaning they are heavily entangled in nature. Normally entangled అంటేనే heavy relation. But when I say maximally entangled, the meaning goes like they are very heavily entangled in nature and these are the belt states. దీన్ని మనం maximally entangled states అని కూడా అంటాము. We will call them as belt states as well. Got it? So that's the difference. Now, Now let's go to the experiment actually. So I mentioned you that entanglement states might they are termed to be breaking the locality and realism and approximate. How did the scientists find out? So there is something called as a Bell measurement, or not Bell measurement, sorry, it's inequality. Bell inequality. So there is something called as a Bell's inequality where the scientist called Bell, I don't remember his first name. I think John or something. So he created a series of tests where he had a lot of inequality methods, out of which the famous one is known as CHSS inequality. What is the meaning behind this CHSH inequality? Ante very simple limit. Limit goes like this. For example, if I take two states, A and B, whose outputs can be plus 1 and minus 1. Ante they can be plus 1, they can be minus 1. They are the possible outputs, like true or false, like an anukon. Okay? But they are not 0 and 1, but instead plus 1 and minus 1. Same B can also be plus 1 or minus 1 accordingly. Okay. So these are the cases. These are the possible answers. A can be plus 1 or minus 1. B can be plus 1 or minus 1. Now, at any point, really, classically, or normally, if you calculate perfectly, yes, A dash, B dash should be 2. Okay. This is the limit actually. Okay. So what is this? And nothing but a simple thing. Now, asal idi enti ante, which I will just explain this one as first, right, this is a limit actually. So really this limit should not be broken. If this satisfies locality and realism. If locality and realism are satisfied, ఒకవేళ రెండు correct, ఆ రెండు satisfy అవుతే, it should satisfy this equation. If these two are preserved, this equation or this inequality should be satisfied. Meaning, if I calculate this entire value, it should be lower than or equal to 2. It is rule. Okay, pakka rule. Okay, that's a rule. If locality and realism is preserved, if these two things are preserved, then this is the rule behind it. Okay, definitely it should be like this. Now, what is this value? And to be honest, so if I take AB, this is nothing but probability of A equal to 1, B equal to 1 plus probability of A equal to minus 1, B equal to minus 1 minus probability of A equal to minus 1, B equal to 1 plus, sorry, minus probability of A equal to 1, B equal to minus 1. ఇదన్నమాట A, B కి మీనింగ్. ఓకే సింపుల్ A, B. సో A, B కి మీనింగ్ ఏంటంటే ఇది. So this is the probability which you guys know already. So probability of A equal to 1 and B equal to 1 value is it. So these are the respective values. And this is the A inner product. Clearly it's not an inner product, but that's the notation which they use at this point. So this is the meaning behind this. Okay. Now, if this is satisfied, the meaning goes like locality and realism is preserved. How it is only 2 and it's a very big meaning behind it. So we don't need to go to very clean mathematics or very clean QM or something like that. But just remember this is the inequality. The inequality is this one. So if I calculate all these values, yeah. So if I calculate all these values, it should be lower than or equal to 2. And where each value is this. It looks like this. Okay. So A, B అని తీసుకుంటే this is the meaning behind it. సరేనా? డాష్ అంటే ఏంటి? కాంప్లిమెంట్. కరెక్ట్. 1 మైనస్ చేసుకోండి అయిపోద్ది. Okay. Now, but when the bell guy he did the measurement by using quantum states rather than your classical states. And a quantum state, in a sense, he did an experiment actually by using the particles. So, which we don't need to go deeper about it. But nothing but a quantum state, simply to put. When he did the experiment, the quantum state, he got the output as this one. Okay, which is greater than the 2, obviously. Okay, but the limit is what? The limit is it should definitely be lower than or equal to 2, right? So if I calculate this value, the output should definitely be lower than or equal to 2. If it is lower than or equal to 2, then these qualities are preserved and it is following these qualities ani artham. Okay, but when Bell experimented and he found the value of this particular thing by using A as a quantum state and B as a quantum state. A ni B ni quantum state can use చేసి try చేసినప్పుడు he got the value as root 2, 2 root 2, which is eventually greater than 2. Thereby saying that, bro, these two are not preserved, bro, and simply to. Meaning this is only not preserved. Obviously, conflict of justice, so not. So thereby, through this, he understood that no, it is not preserving locality for sure. Okay, and thereby your entanglement will not satisfy locality and helps in the Dhinwan. This is the simple thing. Got it? Don't go into deep mathematics like how it is 2, how he got 2 root 2 and all. I was not there at this point of time. Until or unless you want to be an optical scientist or something, you don't require those things at all. Or if you want to go to quantum communications, you don't require these things at all. At this point of time, as a beginner level, at this point of time, you don't require the deep mathematics of it. But this is the entire deal. This is how they found out that this is possible. This is breaking the locality and shift. Advainda, this is known as Bell's inequality. This thing is done, na? Bell's inequality. Okay, Bell's inequality means there are a lot of things. In Bell's inequality, this is specifically known as CHSH inequality. Okay, Bell's inequality means you have something like 2 to 3 types are there. Out of those 2 to 3 types, this is just one of the experiment which is known as CHSH inequality. Okay, a simple deal behind it. Done? Now. Now let's actually go to two of the use cases which we can directly do it by using this entanglement concept. By using this entanglement concept, we can do two of the cases actually. So where my first case is called as super dense coding, and the second thing is called as quantum teleportation. Okay, so there are these two things which we can actually do by using this concept of entanglement in nature. Okay, now first let's start with the super dense coding. Like, what do you mean by this super dense coding? Very clear, very straightforward, very easy. Okay, chala easy super dense coding, and there's not even a single concept behind it. First, let's see the problem. Like, what is the problem and what super dense coding actually satisfies? Simple. First thing, let us say I want to send you two bits of information. Okay, 0 1 no, 1 0 1 1 no, 0 0. Out of these for any one thing, I want to send you. I want to send you two bits of information. How many classical bits do I require if I want to send you two bits of information? We require two bits. So each bit carrying one information, right? So one bit carries only one information. So one bit carries either 0 or it carries 1. So for transforming or for transferring two bits of information, I require two bits, two classical bits. So 0 1 1 0 1 1 0 0. So these four low, any one of the information which I wanna send you. For that I require two bits. Okay. I require classical, I require two CL bits. CL bits ante ente classical bits. Now, but by using this super dense coding concept and which uses the entanglement properties of stuff, we can send these two bits of information by just using a single qubit. Okay, we can send the 2 bits of information by using a single qubit. How, why, we will see. Okay, simply by using the concept of entanglement in nature. By just using the entanglement in nature concept, we can do this particular stuff. How we can do it? Simple. First thing. So what is the entire concept of this, Ante? There are totally 2 qubits in the game. So in the entire superdense coding system, we will be having 2 qubits. Okay, we will be having 2 qubits. And these 2 qubits are, 1 qubit is given to Alice and 1 qubit is given to Bob. Okay, so Alice and Bob are 2 people. If you want to keep, you can keep your own names, not a problem. Keep A and B, Raja Rani, ఏదో ఒకటి పెట్టుకోండి ప్రశ్నే ಇಲ್ಲ. Okay, but theoretically it is Alice and Bob. Okay, so 2 qubits are there in my system which are heavily entangled, meaning I am entangling them in this state. What is the meaning behind this? Which state this gives rise to? 5 plus. Good. This gives rise to 5 plus state. What is the 5 plus state? It is one of the belt state is 0, 0 plus 1, 1 by root 2, which is known as maximally entangled state. If I tell you to create a entanglement state, what you will be doing? First to apply this thing. You will create a first entangled state, simply over. Okay. So I entangle 2 qubits and I will send 1 qubit to Alice and 1 qubit to Bob. Okay. Now the transfer is, Alice should send these 2 bits of information to Bob. Okay, na? Alice should send 2 bits of information to Bob. Okay, now comes the deal here. This is the real one. Okay, it's not just like that. The real thing. Ide cheyali rule. Now 2 qubits are entangled in nature, right? So 2 qubits are entangled. And Alice has Q0 and Bob has Q1. Now, based on the 4 of the states ఉన్నాయి కదా, అంటే 4 states కదా, 4 types of messages ఉన్నాయి, out of which any one thing is being sent by Alice to Bob కదా. 2 classical bits of information, that there are 4 possibilities, out of which one thing. If Alice wanna send 0 0 to Bob, okay, Alice 0 0 అనే స్టేట్ అంటే 0 0 మెసేజ్ ని బాబుకి పంపాలనుకున్నాడు అనుకుంటే, he need to apply any gate. అతను ఏ గేట్ అప్లై చేయాల్సిన అవసరం లేదు. ఓకే, సో this is this one. What is the meaning behind this? Correct. Q0 I, Q1 is also I. ఏం చేంజ్ లేదు అక్కడ, పిక్చర్ లైట్. If Alice wanna send 0 1 to Bob, bro, I need to send 0 1 message to Bob. I don't want to send 0 0 classical bit ని పంపాలనుకోవట్లే. I want to send 0 1 message. If Alice wanna send 0 1 message to Bob, he needs to apply, he or she or ఏదో ఒకటి, she needs to apply X gate. Okay, meaning Q0 లో నేను X gate ని అప్లై చేయాలి. Got it? So the meaning behind this is what? X is applied to Q0 and I is applied to Q1 అని అర్థం. Okay na? This is the meaning behind it. Just keep that in your mind. So if I go like A tensor product, కనిపిస్తుందా? Yeah, okay. If I go like A tensor product of B, the meaning is A is being applied to first qubit and B is applied to second qubit. Okay? If Alice wanna send 0 1 message. Now, if Alice wanna send 1 0, 1 0 message నేను పంపాలనుకుంటున్నాం బ్రో అంటే, she should use Z gate. Okay? If Alice wanna send 1 0 message to Bob, she should use Z gate. And at the last case, if she wanna send 1 1, she should use Y. Okay? So these are the things which should be applied by Alice to the qubits when we want to send any type of message. Okay, na? The entire case is what? Alice want to send 2 bits of message to Bob. Okay, and the 2 bits of message can be 00, it can be 01, it can be 10, and it can be 11 as well. So based on the message which she want to send to Bob, she will apply the gates. Okay, if she want to send 10, she will apply Z gate. If she want to send 11, she will apply Y gate. Alaganmat. Okay, based on the type of message she want to send to Bob, she will apply the gate. Okay, first obviously we will be creating this thing, that is for sure, because they are entangled in nature kada. So first we will create an entanglement thing, entanglement state create chestam, 5 plus vachestade, and then we will apply these things. Got it? Now let us consider she want to send 10. Alice want to send a message called as 10 to Bob. Now what will happen? Which gate she should apply? She should apply Z gate. To which qubit? Q0 or Q1 na? Q0. Good. Here I will apply Z. Okay, that's it. Sorry, that's it. Done. Now the states is being encoded into an entangled point. Now this thing will be sent classically to Bob. Okay, now ఇక్కడ మీకు ఏమవుతారంటే classical simulation అవుతుంది. So I'll just keep like this and I'll write it like classical simulation. Okay, I'll just create a new circuit. So let's just wait a minute. Say Q0, Q1. First I'll create a what? Entangled state. And after creating an entangled, so this is an entangled state. So 5 plus, and then let us consider the messages 10. So here it will create a C gate and the 10 is being sent. Now here I am considering a classical simulation. So what is the meaning of this classical simulation ante? This is entire state is there na? This entire state that will be sent to Bob through classical channel only. Quantum channel అవ్వాల్సిన అవసరం లేదు. నేను classical గా పంపిస్తాను state ని. Which this complete state up to here. From here to here, I'll be sending it to Bob classically. Classically, I sent to Bob. Let us consider I sent to Bob. Big పంపించేసాను. Now what will Bob do? Bob will do something called as bell measurement అంటాం దాన్ని. Bob will perform something called as bell measurement. So what is known as bell measurement ante? Reverse the 5 plus entanglement. That will be bell measurement. How you are going to get 5 plus? 5 plus ఎలా achieve చేసాం? Here in the circuit. You applied a Hadamard gate and you applied a C0 gate. Kada? Bell measurement is a reverse operation of 5 plus gate. Meaning what you will be doing? First you will apply what? C0. First we will apply C0 gate. First I will apply C0 gate. And then what I will apply? I will apply a Hadamard. Sorry, circulation. That's it. So this particular concept where I'm applying the reverse 5 plus gate is known as my bell measurement. Okay, I will do this and I will simply measure it out. I will get the, what can I say? I will get the answer. Now I will do measure all. Actually, now after doing this, what I will be doing? I will be doing performing my measurement. So what is a measurement? So what is this signifies? This signifies the presence of classical bits. Now what I will do is simply perform the measurement. Got it? So this is how I will create my super dense coding circuit in order to send which information, which classical bit is being sent by Alice to Bob in this circuit. Correct. 10. So this information of 10 is being sent to Bob from Alice. And this is the circuit for that. Okay. First, create an entangled state. Okay. First case when an entangled state will be created. And after an entangled state is created, based on the information Alice wanna send to Bob, she will apply the gate. If she wanna if she wanna send 10, she applies Z gate to Q naught. Okay. And then this prepared state she will send in the with the true classical something to Bob. And after this state is being received by Bob, what will happen? He will apply something called as a Bell measurement. Bell measurement is the reverse of your 5 plus state preparation. Okay. And it is a C naught followed by a Hadamard because 5 plus NT Hadamard followed by a C naught. Reverse C naught. And after doing the Bell measurements, he will simply measure them all. That's it. He will measure Q naught, he will measure Q1. Q naught of a measurement is 0 keltari, Q1 of a measurement 1 keltari. IPN. Now if you see the output, the output will be in a probability of the states where 1, 0, right? It will look something like this in the graph. Graph it will look something like this. So this will be here, and let us consider this here. This will be here, and this can be here. So this is how the output and probabilities look like. And this is state. So this is how it looks like. So where the 1, 0 is having, oh sorry. So I'm sending 1, 0, right? So it will be like this. Yeah. So if I'm sending 1, 0, I'm sending the information of 1, 0. Okay. As I'm sending 1, 0, this guy will show heavy probability. Why? So what I'm sending a classical bit of 1, 0 kada. Nen pampedi 1, 0. But if you perform this circuit and if you visualize the output, the output will look something like this. Why I'm sending 1, 0, right? Why 0, 1 has heavy probability? 1, 0 should have heavy probability, right? Why? Because simple. Answer is 1, 0 only. But when doing this thing, what will happen ante? It will take the values in this way. Okay, so it is not 0, 1. It is 1, 0 only. It is 0, 0. It is 1, 0. This is 0, 1. It is 0, 1. It is 1, 1. So why? Because it will read in the reverse order when you are actually finding the probabilities. Sarena? So this is your super dense coding. Okay. So yes, I think the time is already up for me. I'm running 2 minutes late. So yeah, I guess I will just conclude my session till today. So till here. So yeah, thank you for giving me this opportunity. Thank you.
Thank you so much, sir, for the truly enlightening and thought provoking workshop. The entire workshop is for sure a damn hit on quantum algorithms and hybrid machine learning. It was such a perfect way to set the tone for any days in the Qiskit Fall Fest. And what do you say, guys? I would like to say Dr. Jnan sir undoubtedly deserves a humongous round of applause for all his efforts, the time he have taken for us, and the patience and generosity he showed. This is by far the best workshop experience for all our attendees, sir. Really, thanks a lot.